Hey there, this is Seth Schaefer from Team Just Cause Robotics. This will be a continuation of my discussion on combat robot spinner design, and here I'll be talking a lot more about how I actually go about physically designing the weapon in CAD and then verifying that it will work using simulations and finite element analysis. If I sound a bit different, it's because I'm using a new microphone to record this intro, but I recorded the rest of the footage at the same time as part 1, so you'll be hearing my voice just the same as it was in part 1 from now on.
Alright, so like I was saying, egg beaters get close to being most optimal possible shape for MOI because they have so much mass on the outside, but it's still a single material as opposed to having like teeth bolted onto, like a steel tooth bolted onto an aluminum drum like what Yeti has. Which means that it's like a stronger shape. A hollow disc, like with mine, the same idea as an egg beater, kind of just getting the mass towards the outside, though as you can see I did better job with that with this design versus this design, but still, because I need such like relatively thick spokes compared to the thickness of the ring though, my design isn't nearly as weight efficient as like if you have a huge tube where that is like the wall thickness making up most of the mass, as opposed to here where I have possibly like equal mass in these like ring sides as I have in the spokes and the teeth themselves. And then solid disc is considerably worse than a spoked outer ring because it needs to be super thin for the same weight, and also because the average position of where the mass is going to be like in the middle. Here I tried to push it further to the outside, though because of the spokes it didn't necessarily accomplish that perfectly. But because the average distance from the central axis is going to be like kind of in the middle there, it's not the best. A bar is much worse though generally. And then asymmetric weapons are harder to design and keep the center of mass on the central axle, but they have advantage of double the byte for the same RPM, like I was saying. Designing one is a lot of trial and error and just making small tweaks until it's perfectly centered. I don't really have any special tricks for doing that other than that. Having an asymmetric weapon with double the byte means you can double the RPM and get the same byte, which means you get 4 times the kinetic energy with the same byte, so that's obviously great. But balance is key, as always. Other things, you want to avoid stress concentrations, which means using generous fillets everywhere. You can see these fillets are like absolutely massive that I have on Division's weapon. Especially like here, and then also back here, where a lot of the stress will be from the hits. You also want to think about how you're going to drive it, so pulleys, hub motors, live or dead shaft. I would say the vast majority of vertical spinners for sure use a dead shaft. I don't really know for horizontal spinners because I don't know how you accomplish a dead shaft like really effectively with a horizontal spinner if it's an undercutter, and a lot of them these days are, but you can definitely do a mid-cutting dead shaft like what Tombstone does very easily. Dead shaft simply means that the actual like rotating elements of the weapon are like on bearings, and the shaft that they're on doesn't rotate. In my case, I have, I don't know what you call it exactly, but something in between a live and dead shaft where this shoulder bolt is the weapon axle, and it doesn't spin at the same speed as the weapon, but it is able to rotate like semi-freely. Like I don't clamp it down like really fixed, because otherwise it would clamp these 2 sides onto the weapon and it wouldn't be able to turn at all. So that just kind of helps reduce friction a little bit more, but it's obviously less rigid like side to side. Bearings or bushings. Basically, bushings are really cheap. You can use oilites for like a couple bucks a piece. The bearings I'm using in Division are actually a couple bucks a piece too, but when I went up to making my hobby weight, there was no way I was going to use bearings because A, they're gigantic like radially, and B, they cost a lot more when you're talking about running a bearing on a 3/4 inch shaft. Here it's a 3/8 inch shaft. So I ended up getting $3 oilite bushings, and because my weapon's running at less than 10,000 RPM, that's like not a problem. I've heard of people using oilites at like 30,000 RPM, but like generally I wouldn't recommend running a bushing of any kind over like 10,000 RPM. And also you can get thrust washer versions of oilites, or you can get like needle bearing thrust washers as well. Those, I think, there's a little bit less of a major advantage to using the needle type over the bushing type, because unless your weapon's constantly being pressed against it, like there's not going to be a huge amount of heat buildup from the friction there. But it's like the difference between using bearings and bushings, it's really a question of, is your weapon turning fast enough that the heat buildup will like cause significant problems if you use a bushing? If not, go for it. Otherwise, you have to use bearings, so just do it. And then also, if you're trying to get something that takes like ridiculous, like twisting, like torsional loads, a bushing's not going to do as well as like angular contact bearings or even tapered roller bearings if you're like super hardcore and in like much larger weight classes generally. Actually designing a weapon. So designing a weapon, like I was saying before, it's like an annoying balancing act because there's so many different variables. Generally what I would say is design the rest of your robot first. Like Ask Aaron says, your weapon is like the least important part of your robot. Reliability is really like the #1 thing that'll get you to win fights, and that's like Division's been doing so much better lately because I just keep iterating and iterating and iterating to improve reliability and almost nothing else. Like you can see right here, it pretty much says up at the top, I think, somewhere in here, that the weapon is like the least important part. Yeah, right here. The weapon may be the least important part on your combat robot. If you're not winning matches, it isn't because you have a poor weapon design. Drivetrain, radio setup, and general construction practice are way more important than the weapon you choose. So I would say definitely design the rest of your robot, keeping in mind what kind of weapon you want, but not like designing the weapon from the start and then build your robot around it, because that's probably going to lead to you making like huge sacrifices elsewhere. So design a chassis first that drives and like will work, and then add the weapon with what weight you have left. And that way you'll know off the bat from the chassis what diameter your weapon's going to be, how much weight you have to dedicate to it, and that kind of takes away 2 of the several variables that you have to play with. And then that weight budget will also kind of tell you what kind of motor you can fit in it, so you'll be able to choose a motor that effectively gives you what rough like RPM range you could be running at. So in my case, I'm using like a really, really, really tiny pulley on the motor and a really, really big pulley on the weapon. So I have like a 3-to-1 ratio, but that's pretty much the highest ratio that I've heard of people doing with like a single reduction in a weapon robot. So I would say like you're not going to generally want to do like a 3 to 5 times ratio for pulleys and belts, or especially chains. You're probably going to want to stay kind of close to the motor RPM, but I strongly recommend that you pick the highest KV motor that you can for a given model weight, and that's simply a matter of power to weight. So I actually did a web scrape on a website that has a shitload of brushless motors. So right now I have this sorted in the current rating for the motor per gram of weight of the motor, and you can see this distribution lines up very, very well with this distribution. Higher KV motors generally have much higher power to weight ratio, and especially if you go to Hobby King and you look at the motor that I have in my robot, prop drive 2836 3000. So this motor is available in a bunch of different KV ratings, if it will load. So this is rated at 55 amps. If we go to the 2836 2200 kV, it is rated for 50 amps. A bit lower. What about 2836 1000 kV? It's only rated for 30 amps. So your power to weight, the motor weighs the exact same, but the max amount of power that you can get out of it has been cut from 55 to 30, almost in half. So you're not doing yourself really any favors by using a lower KV motor at like a 1-to-1 ratio over using the motor that I have at a 3-to-1 ratio. I strongly would recommend against using the lowest KV for a given model motor. Definitely want to go for the highest if you can, or like maybe the second highest or something if it's not a drastic difference. But like if a motor of a given size is available in 6000 kV, 2000 kV and 1000 kV, you're gonna want to use the 6000 kV and make whatever changes necessary to run your weapon at a reasonable speed from that. It is still important though that you gear it down so that you're not running your weapon so fast you get no bite, and also have no torque to spin up. So yeah, RPM, it's gonna be variable, but not by a ton. You're gonna want to use the highest kV you can. Again, like I said before, your RPM and your forward velocity are what determine bite, so, and how many teeth. So like, if you know that you're gonna be doing a 2-tooth weapon, like the vast majority of them are, then that will pretty much tell you what RPM range you want to be looking at, so that you aren't sacrificing bite too much. Bite's critical. You probably want at least a 1/4 inch of maximum at full speed forward velocity and full speed weapon. Depending on your design abilities, you can try a single tooth weapon, which means double the bite, the same bite, double the RPM, or in other words, you can quadruple your KE, but at the cost of lots and lots of gyro. So like, the more KE you have, the more gyro you have to deal with for a vertical spinner. That's like the main trade-off, is simply that the more MOI that you have in your weapon, the more KE that you're building up in the weapon, the more gyro that you have to deal with for a vertical spinner. For a horizontal spinner, that like basically doesn't matter at all, so pretty much just like maximize KE as much as you can, it seems like, as long as you won't break yourself. And then the only downside to MOI to weight is the higher gyro forces at the same RPM. So that's why if I'm fighting a wedge, I'm probably going to switch to the bar because it has less moment of inertia. But A, I get a positive rake angle so I can grab onto wedges more easily, and B, I can run the weapon at the same, at like a higher speed and still be able to turn effectively than I could with the higher MOI weapons. And then higher MOI to weight can be a lot lighter but still hit just as hard. So I wrote here example kinetic drum. So kinetic kits are these guys. You've probably seen these at competitions if you've been to a few beetleweight competitions. They're pretty popular. It doesn't say what the RPM of this weapon is anywhere, so I literally have no clue what it is, but I'm just going to assume, for the sake of example, that it runs at twice the speed of Division's disc, 24,000 RPM. So I created a model of the kinetic kit drum based on literally the no information that they provide, and me just deciding to like say F it. So if you look at kit and subparts here, it tells you they use 5/16-18 steel screws for teeth, and that the weapon is 7075 T6, and it is 3/4 inch thick, and somewhere or other I saw that it was 2.5 inches by 3.859 inches, something like that. I don't know which page exactly said that, but it was definitely here somewhere. Anyway, so I drew up a model of the kinetic kit, like beater bar thing. So this is like an egg beater, so you'd think it's really MOI efficient, but the problem is that it's aluminum, so it's really, really, really light. This is by no means an official CAD model for this, and it's probably inaccurate, but it gets the point across. So I have some alloy steel screws, they're set to steel material. I have this thing, which is set to 7075 aluminum material. And if we look at what the moment of inertia is about the x-axis, IXX is 1.129. 1.129 times 10 to the 5th. So even if we double the RPM, we're at less than 400 joules. So my bar weapon, which is my least MOI efficient weapon, at 12,000 RPM, has more kinetic energy storage than a kinetic kit drum at 24,000 RPM. That's insane. And on top of that, this is still a like symmetric 2 impactor weapon. So they get like no bite when they're running at max speed. You see this all the time in competitions, that these drum spinners will run at full speed and just try and drive into people as fast as possible, and they still like grind against like pretty much any wedge in the world without getting any bite, because there's just no way at such a high RPM when you have like 3 millimeters of maximum tooth engagement. So I designed Division's weapon to be really, really big so that it has a lot of kinetic energy at a much lower speed, but I can still run it really fast at like a 250 mile an hour tip speed roughly, and like deliver really, really big hits because I have this feeder wedge. The other huge disadvantage to bite that the Kinetic Kit has is simply that it doesn't have a feeder wedge. So that's like the other real problem, and that's why these forks are here, is to try and mitigate that a bit. But like, what angle are those forks at? For every linear inch across these forks that an opponent moves horizontally, they move up vertically like 1/8 of that. My front wedges are at a 50-degree angle, so I believe it's 50, it might be 55. Bam, 55, okay. So 55 degrees, that means that if my opponent drives 1/4 inch into my wedge, they are driven up more than 1/4 of an inch into the tooth. So my feeder wedge is a lot more effective than these tiny piddly forks on the Kinetic Kit. One other thing is the fingertech feeder bar. I've seen these a number of times in different competitions. So this, it tells you a lot more information about it. So I could probably get a more a more close to real life calculation for exactly what the MOI of this is. But again, like, I don't know exactly what speed people are usually running at them. So I figured, and also this is a pretty hefty like weapon assembly, but they factor in the shaft as well in that. So it's 11 ounces, 11.4 ounces for this whole thing. But that shaft is probably a significant portion of the weight because it's steel, and this is 6061 aluminum. So, you know, take what you will from it, but I am willing to bet that, again, this is running at like twice the RPM of my disc and thus getting a tiny, tiny portion of the bite. So yeah, that's pretty much all that I wanted to cover in terms of the theory behind it. I'd like to at least briefly pull up the simulations that I was doing to get a general sense of like, will my new spinners still survive hits? So this is those. So I did these in SolidWorks because I decided to use my work computer to design the asymmetric weapon, since it was a lot easier to do the center of mass like position calculations and stuff, and like really quickly iterate it. But you can do the same exact thing in Fusion 360, it just takes a bit longer. So let's start with the disc. I have like some of these in different scales. So this is a factor of safety plot in SolidWorks. It's a lot less blocky than it is in Fusion. So factor of safety here, the minimum is factor of safety of 3, and again we're seeing it right at the screw holes on this disc. This is a modeled 100-pound static load on this like block, just so that I could get like not the entire surface area of the side here. SolidWorks doesn't have a way to do a point load the same way that Fusion does. And so you can see here I've switched to stress view. So this actually, like, here it looks like everything's red. It's so terrible. Like, really the stress concentration is like just that little tiny lip on the screw face. And even then, I'm getting a factor of safety of 3. So like realistically, my factor of safety is far higher than that for this design. This is an exaggerated view showing the deformation of the disc under this load. So this is a deformation scale of 10 to 1. So this is definitely not actually going to bend like that far. You can see this is the scale, so that very, very point here is moving 1.19 millimeters in real life under this 100-pound static load. So when I'm getting hit by another robot, it's not going to flex so much that I'm cutting my belt or hitting my own pulley anymore. Here's a side view of the same exact thing, 1.19 millimeters of flex. It looks terrible at 10 times scale, but in real scale, it's like nothing. So here's the S bar, showing the same exact thing, 100 pounds against the tip. Here it's deflecting only 0.979 millimeters. Again, at 10 times deformation scale, it looks really terrible and what have you. And then here is the new weapon design. So 1.15, pretty much the same as the disc, 1.15 millimeters of flex. Okay, so now let's get on to the stress plots. So here, I did some ISO views. Yeah, so here is a factor of safety on the S blade. Here it says the minimum is 4.18, but again, it's like a tiny little edge, and it's not really a big deal. Here is the factor of safety plot on the new weapon design. You can see again I'm at the screw holes, just like with the disc, at 3.44, and then same thing. And here I did an ISO view. So this is the new weapon, the like Deep Six style weapon. So you can see how little that's like penetrating into the material again. So like in real life, that 3.44 is like kind of underestimated because it wouldn't actually like yield throughout. It won't like crack or whatever. It won't permanently bend. And then here you can see even more dramatically where it's like the absolute highest stresses. This was factor of safety. This is stress now that we're looking at. The actual stress concentrations are again like at these edges of the fillets and the edges of the screw holes. And stress plot again. So here's the factor of safety with a scale going up to 100 before the scale went up to 20. So that's why everything looks so much worse, but it's actually showing the exact same information as before with the same exact, or slightly different loading conditions. I think I just applied the force to this whole face. This is like less properly representing what's going on. And here, same exact thing. So stresses from the blade, and then this is factor of safety again scaled to 100 instead of 20, so everything looks more red. But yeah, it's still like factor of safety of 4.18 minimum, so that's like not a big deal. And here's the part where I'm simulating like my weapon hitting an opponent. So in plane forces, and you can see that there's a lot less red. This is factor of safety up to 20 again, but still, like, it's totally fine. Here, same deal with the blade. Basically only the little bit of the tooth at the tip that might chip is in red, and everything else is totally fine. And then the brand new weapon, doing the same thing. You can see that the maximum stresses are in those fillets. That's not a very accurate plot. Factor of safety up to 100 again. Stress plot again. So yeah. I didn't do too many simulations with the disc weapon, but you get the idea. Like, the difference between them is not drastic in terms of like what forces they'll survive, but like my blade definitely resists impact forces probably the best, which is why I would use it against a horizontal spinner most likely, and why I did use it against horizontal spinners several times at Norwalk. It's much less likely to like fail since there's just so much like thick material there compared to the disc. And this new weapon is kind of like an in-between. So it should be able to resist a horizontal spinner hit better than the disc, but it won't be as good as the blade. And again, because these max stress concentrations are at the screw holes, like, it's probably not going to be failing like the disc bent against that horizontal I fought at sword. I don't think it'll be as easy to break this new weapon design as it would be for the disc. Doing simulations like this, once again, it pretty much only provides you with comparative results, which is why I'm showing comparative results here between all my 3 weapon designs, and I am not pretending that this is 100% accurate to what will happen in a fight, because no one can possibly know that. So yeah, I hope that answers all of your questions about spinner weapon design. If you have any more, please feel free to leave them in the comments. And I hope to see you guys in the next one.